Okay, let's start. Folks, conversation's over. Okay, so last time we talked about the classification problem, and we laid out basically the motivation behind the hard margin SVM, right? How do you make sure that you can have a separating hyperplane such that there are absolutely no margin violations, right? You don't want errors on any of your points. And then we said, of course, that's kind of completely unrealistic. In any data set, you're going to actually have noise, and therefore you're going to have some kind of violations. You're going to have some things that don't classify perfectly, right? And that motivated us to set up basically the soft margin SVM. And what was the formulation for this? Well, we said we want to minimize over W and B and the psi i's. And we had the same thing as kind of this came from our hard margin SVM formulation. And then we had the constraints yi times W transpose xi minus b greater than or equal to 1 minus phi I for every I. So the hard margin SVM, we had this thing greater than or equal to 1. Remember? But for the soft margin, we said, well, we're actually willing to allow some violation. And we allow that violation to be psi I. We want that to be positive. So we have this constraint psi I greater than or equal to 0. And then we also want to have some downward pressure to make sure that these psi i's do not become too large. So we had this regularizer here. Right? We had one slack variable, that's what we call these psi i's, for every single data point xi comma yi. Okay? Everyone remembers this kind of formulation of the soft margin SVM and why we did it? And then we saw that this parameter C basically allows us to smoothly go from the hard margin SVM to the soft margin SVM, or really vice versa, right? When C is really, really large, right, what does that mean? It means that you're absolutely not allowing any margin violations at all. And so you're really pushing towards the hard margin SVM solution. On the other hand, when C is small, well, then you're allowing lots of violations, right? Because you're not penalizing these violations very much. And so by changing the value of C, you can basically tune how permissive your classifier is, okay? And C was a hyperparameter. It's not something that's specified. It's something you tune to kind of get the performance that you desire in your particular application. Remember, we looked at the demo and we saw that as we changed the value of C, we had more and less margin violations in that case? Yes? Everyone with me on this? Okay, good. So now, one of the things that many of you asked about was, well, why this particular formulation, right? Like, well, maybe you could regularize with something else. Like you could regularize with psi I squared. Would that be a valid formulation? It would, right? We made choices along the way. And we made choices. For example, we chose to add this 1/2 over here. And you'll see the reason why we do that, but it's basically to make calculus easy later, right? But could we have done the same thing without the 1/2? We could have generally achieved the same high-level objective. And as you saw, we went through many different formulations of the same problem to get to here, right? This particular formulation is the standard one and is the popular one for multiple reasons. One of the reasons being that there's actually many different interpretations of this particular optimization problem. And so another interpretation of this problem is I want to introduce you to the hinge loss formulation. Of this problem, okay? So in general, I'm trying to classify my points, right? And I'm classifying my points. I'm looking at this quantity yi times f of xi, right? Y is the label, and f is my classifier. If f is positive, then I label my point +1. If f is negative, then I label my point -1, right? In our case, we had f of x I equal to w transpose xi plus b, right? We wanted to find a separating hyperplane style classifier. So when we're looking at this, we can think about loss functions that are directly a function of this, right? Basically, did you get it correct or did you not get it correct? When is the point correctly classified? If yi times f of xi is positive, right? That means that the point is correctly classified. And so we have basically what we can consider a standard 0-1 loss, which is that says that if I have this axis yi f xi, this is my x-axis here, then I can consider the following loss function. Maybe I'll use color here. This is my 0-1 loss function, which says that, hey, I'm going to give you a loss of 1 if you get it wrong, and I'm going to give you a loss of 0 if you get it right. Pretty basic, right? And so if you wanted to come up with a classifier, this might be a natural loss that you would want to minimize, right? Basically, get the points right. What is the problem with this loss function? It's not differentiable, indeed. We don't like that. What's another thing about it that we don't like? It's not convex, right? I could take a point here, take a point here, draw the chord. Is the chord above the function? Nope. So we don't like non-convex things. We're lazy. How would you convexify this loss function? A convexification of this loss function is what is called the hinge loss formulation. So basically what I say is I'm going to consider the following loss. Okay? I'm going to consider this orange curve. And here, if I now use this loss function, this is saying, look, I'm going to give you 0 loss if yi times f of xi is greater than 1, not greater than 0. So I'm taking a loss. I'm taking this little bit of loss here, even though I've classified correctly. And as I go more and more negative, I'm penalizing myself more and more and more. Okay? It's called the hinge loss because it looks like a hinge. Okay? That's why it's called the hinge loss. But this is a standard convexification of the 0-1 loss function, right? You can see that this function now is convex. It still has this non-differentiability here, but at least it is convex. Okay? Does everyone understand this hinge loss? So if I was to make, I could put this hinge at different points, and there's different trade-offs, right? But this is incentivizing me to kind of have things be away from the boundary, right? Having something that's very close to the boundary is something that I don't necessarily want. So it's saying push things away from the boundary. But if I was to now try and write this mathematically, well, how could I write this hinge loss as? I could write L hinge, right? So this line here is basically, it has slope of, it's basically -1 slope, right? It's like minus y times f of xi, but it's shifted. So it's like I have 1 minus yi times w transpose xi plus b, right? This is that line, that orange, the line, the negative slope line. But then what happens when it hits 1, when yi f of xi, when this quantity is equal to 1, what does the function change to be? What is the value of the function? 0. So does this function ever go negative? So I can write this hinge loss as the max of these two quantities, right? This is your loss as long as it's positive. As soon as you go negative, just hit the floor of 0, right? If this is positive, this will always be the max. If this quantity is negative, 0 will always be the max. Do you see how this function gives you exactly that hinge loss curve there? Everyone with me? OK, good. So now I can think about kind of formulating my problem as minimize this hinge loss. So I have my points. And what I'm going to write this as minimize over W and B, 1 over n. And then I can say, well, this again has the same problem for W and B that we had before, right? That multiple hyperplanes are represented by multiple pairs of W and B. And so we discussed multiple different choices for how we could avoid this problem. We chose a particular one the last time. This time we'll choose a different one. I'll add a regularizer to make sure that the norm of W is small, okay? So this is my hinge loss formulation, and this you could think of as yet another way to classify points, right? I'm saying, look at my points, try to make sure that they're always correctly classified, because if you're wrongly classified, your hinge loss is going to go up, okay? And do this while making sure the norm of W is kind of small. Okay. So let's now look at our soft margin SVM over here. Let's compare these two things. So I'm going to rewrite this a little bit, and I'm going to write it as min of 1/2 Okay? I just rewrote this second condition by just changing the order of the where everything is. So now I have this condition as psi I greater than two things. Can I combine this to instead write max of this and 0, right? It needs to be greater than both of them, so it clearly has to be greater than the maximum. Okay? And now, if I further think about this, what do I have here? I have basically a lower bound on this psi I. And I'm trying to minimize this quantity, right? So at optimality, just the same way we've been making arguments for all of our slack variables, what is the value of psi I going to be equal to? We have always pressure to move downwards, right? So I'm always going to end up choosing a value for psi I that's exactly equal to this lower bound at optimality. Because if I didn't, I could reduce my objective function, right? So at optimality, and so I can rewrite this as the min over W, comma B, 1/2 right? I just replace psi I by the bound. But now look at this problem and the hinge loss formulation. It's exactly the same up to constant, right? And by choosing c and lambda appropriately, you can just basically you can reformulate one into the other, because all that matters in this optimization now is the ratio of these things, right? Here you have a 1 over n and a lambda. Here you have a 1/2 and a c. Okay? So as long as the ratio of 1/2 to c is the same as the ratio of lambda to 1 over n, these problems are entirely equivalent. Okay? So this SVM formulation, we derived it one way, but you can also think of it as this other way of classifying things. Okay? In contrast, for example, if you were to do logistic regression is also another technique for classifying things, but that formulation is not equivalent. You will not get the same classifier, because logistic regression is fundamentally trying to do something different, right? It's trying to give you a probability. And so it will classify, but it will do something fundamentally differently. This is showing that these problems are equivalent, and that's one of the other reasons that, for example, we like this formulation on SVMs. No, okay? C is corresponding to the 1 over n there, so I'm not sure. Would using logistic regression and kind of setting a cutoff point for classifying result in the same answer? Not necessarily, because it's fundamentally optimizing something different. If you have the same training data, you're probably going to get some similarities because you're training on the same thing, but it's fundamentally trying to do something differently. So I wouldn't necessarily say that, these things are they're not equivalent. They're different. They're different methods for classification. There's not that one's better or worse, or they're just different. So now we talked about kind of this one example for the support vector machines. What if I had the following very simple one-dimensional example? I have my triangles here, and I have my circles here. And I want to be able to classify these, okay? If I had a hard margin SVM, where would the hard margin SVM put the classifier in this picture? Right in the middle of what? In the middle of these guys? No. Which two guys would matter? These two, the closest guys, are the only guys that will matter, right? Everything else is kind of irrelevant. So this midpoint is the hard margin SVM. Right? What if I had this, and then I had this data, but maybe I got like another triangle here, right? If my data was instead like this, now where would my hard margin SVM put the classifying boundary? It would put it here, right? Which, maybe is a good idea, maybe is not a good idea, but this does seem kind of like an outlier, right? It seems like a noisy point. It seems like maybe there was some error, some noise that pushed it there. What a soft margin SVM could do is it could say, well, this is the thing that I'm going to allow for a violation, and it could still allow for your boundary to be somewhere on this side, right? It might not choose exactly this, but depending on what hyperparameters you choose, it may or may not allow you to have this triangle as a violation, right? So if I got this point here, like as extra data, like clearly my margins are going to change, my classifier is going to change. But what if I added like some more circles out here? Does this affect anything? It doesn't at all, right? Or more triangles out here. I could keep adding data, and as long as that data was not particularly close to the boundary, my classifier would remain exactly the same, right? And in reality, what you can see is that even though I might have a huge amount of data, right? I might have millions of points on both sides of this. How much data does my classifier depend on? Very few points, right? In particular, 2 points in this particular example. This is another example of sparsity, right? The dependence is on these very few points, and this is a feature in a sense, right? Because it allows you to basically have this classifier train on lots of things, but then be representable using just a very few, right? And this is useful for your memory, like for just making this thing more easily implementable. And these things that your classifier actually depends on, these are what are called support vectors, basically. And what we're going to do next is now do a rigorous derivation, of our formulation to identify what the support vectors are, right? Because if you knew exactly what the support vectors are, you don't need to carry around a huge data set anymore. You just need to keep track of those few support vectors, and you can always get your classification boundary, right? When a new point comes in, you just have to evaluate, is this going to be a support vector or not? Okay? Does that make sense to everyone, what we're going to try and do? Okay. So in order to proceed on this agenda, what I want to do is I want to now consider the dual of the soft margin SVM. Okay? I'm going to consider alpha and beta as my dual variables. And they're both greater than or equal to 0. Okay? So let's now look at our Lagrangian for this thing. Okay? And I'll use the original formulation up there, not the one that's kind of massaged to look like the hinge loss. But if I write my Lagrangian, this is now a function of w, b. I'm going to just call this a vector psi. Right? I'm going to take all of my psi i's and stack them into this vector psi. Everyone okay with that? Alpha, beta, right? This is my Lagrangian. And this is equal to now 1/2 norm w squared plus c times sigma psi I plus now I'm going to consider this constraint as written to be greater than or equal to 0, right? Or sorry, less than or equal to 0, because that's always how we write our constraints. Remember, when we think about duals, we always write our constraints as fi of x less than or equal to 0. Right? So I'm just going to rewrite that, and I'm going to think of this as plus some alpha I 1 minus psi I plus yi times w transpose xi plus b, and then plus beta I times minus right? So I have my objective function here, and then I have my 2 inequality constraints that I've now multiplied by my dual variables and added to my objective, right? Kind of standard bread and butter vanilla writing of the Lagrangian. Nothing fancy done here. We're good? Okay. So now I want to try and find the dual. And what we're going to see here is a different technique for finding the dual than we've been doing so far, and a different use of the KKT condition. So we're really pulling together in this lecture and every single thing we've done in the class so far. So just as a reminder, recall right, that if I have P star equal to, now I can write this as a min max. So let's say this is a min over x, max over lambda of L of x comma lambda. And let's say I know strong duality holds. Okay? Then I can write the dual as the max over lambda min over x of L of x comma lambda, right? I can obtain the dual by switching the max and the min, right? We kind of talked about this way back when we were talking about duality. Okay, good. So I want to use this property of duality. And the other thing I want to do is I want to use the KKT conditions. Okay? Did I get a sign wrong? So I want to have 1 minus psi I minus yi. Thank you. Minus b. No, this should be, I mean, we were thinking about our f as this, right? It just doesn't really matter, but I think this is fine. Yeah. Sorry, yeah, that should be negative because I want to have this whole thing less than or equal to 0, right? So 1 minus psi minus yi times f of xi should be less than 0. Everyone see that? My typo? Okay, good. Okay, so this is the Lagrangian. Now when I look at my optimization problem over here, we identified last time that this was a quadratic program, right? The objective was quadratic, and the constraints were just linear. They're affine constraints. So now, basically, we can conclude immediately, because the constraints are just affine, that strong duality holds, right? It's a convex problem, so Slater's condition applies. But because you have no nonlinear constraints, your only constraints are linear affine constraints, you don't need to check for strict feasibility of anything, right? So basically, you know in our case that our problem is convex, affine constraints, and so strong duality holds. Okay? So we are able to use this kind of technique to be able to find our dual if we wanted. Furthermore, because strong duality holds and we have this nice convex problem, our KKT conditions are both necessary and sufficient. So we know that any optimal point must satisfy the KKT conditions, and if a point is optimal, it must satisfy. If a point is optimal, it must satisfy the KKT conditions, and any point that satisfies the KKT conditions must be an optimal point, right? That's what it means to be necessary and sufficient. The implication goes both ways. Okay? So what we're going to do now is we're going to use the KKT conditions to get some properties about how the primal and the dual variables are related to each other, and then use those to kind of massage our objective function and massage our Lagrangian to be able to then finally get the dual. Okay? So it's like a way of finding the dual by using the KKT conditions, which we haven't yet done so far. So it's a kind of it's a new technique in that sense. Okay? So I want to really just first focus on the first order conditions. Okay? And what are the first order conditions? Well, I have three primal variables, right? W, B, and psi. So I'm going to take gradients of the Lagrangian with respect to them. And these must all be equal to 0, right? That's the first order condition from the KKT conditions. Everyone remember? We have primal feasibility, dual feasibility. Then we have the dual variables, and then we have complementary slackness, and we have these first order conditions. So, okay. So I'm going to write the gradient of this Lagrangian. So now this is where my 1/2 pays off, right? So what is the gradient of that first term with respect to W? Just W, right? Now I don't have to carry a 2 around here because I put that 1/2 there before. Okay. And then I have, where else does W show up? It doesn't show up in the second term. It only shows up in the third term. So I have, for every W, I have basically an alpha I, yi, xi term, right? So I have minus sigma alpha I, yi, xi. Okay, and this must be equal to 0, which implies that at optimality, my W star is equal to alpha I, yi, xi. And this is kind of a nice formula to look at in and of itself, right? Because what is this saying? This is giving me W is just a linear combination of my training data, right? And the dual variables are the weights of that linear combination. So it's particularly nice. And now, if I had hundreds of millions of data points, but only 2 of them were relevant, this sum is actually quite small, right? The number of entries in this sum is actually quite small. So wouldn't it be nice to care only about a few of these i's, right? As we saw in our example up there. So just keep that in mind as we're going forward. So already this has given us some nice structure that might come across, okay? The next thing, my next variable is b. So I'm going to look at, b is just a scalar, so I'm just going to look at the partial derivative. Nothing in the first term, nothing in the second term. In my third term, what am I going to get? B is basically, I have an alpha I that multiplies B, and I have a yi that multiplies B, right? So this is equal to minus sigma alpha I yi equal to 0, right? Which I can just rewrite as the minus sign doesn't really matter, right? From setting this equal to 0, this is what I get. And now the third thing, I'm not going to take the gradient with respect to psi i's. Instead, I'm going to take the partials with respect to every single. I'm not going to take the gradient with respect to the vector psi. I'm just going to take. It doesn't matter which one I do. This is just slightly more convenient for the kind of calculations that I want to do next. So when I look at psi I, it's not in the first term. Is it in the second term? Is that going to show up? What is the partial there? What term am I going to get here? C. Okay. Then where am I going to get psi I next? I get, what's the coefficient in front of it? Just to make sure everyone's with me. Everyone shout it out. Be loud. Okay, minus alpha I. And then what am I going to get next? Only at the end, what do I get? Minus beta I. This is equal to 0, right? Summation. No, because I'm taking this. I don't want to take it with respect to the vector. I mean, I could just stack this and write this as a vector, but this will make it easier for me to do some calculations later on, which is why I'm writing it element-wise instead of as a vector. Okay? But basically, if the gradient of this with respect to of L with respect to the vector psi is 0, all entries of it must also be 0, right? That's all that I'm saying here. Let's substitute this back in. So let's now consider the Lagrangian W B psi alpha beta. Okay? Which I have up there. And now I have this 1/2 norm W squared. Okay? I'm going to keep that as is. What do I want to move next, actually? Let me think. How do I do this strategically? Maybe I want to do a little bit of grouping of terms, actually. That might make my calculations slightly easier. So let me pull out this term. So minus sigma, let me pull out all the terms that have w's in them. Alpha I yi times okay, so I've pulled out this other term with a w. Are there any other terms with w's here? So I have this term and this term are the two terms with w's, right? I've put them out first. Okay, good. Then I have, let's pull out, I have this sum of alpha i's. Right? And then everything else has this, everything else is a term with the psi I in it, right? So I have psi I from the second term, alpha I times 1 minus psi I, I'm just pulling out the 1 there.
Oh, I see.
Right? Over here. This term up here. Okay? So all I've done is I've rearranged these things to have like kind of the w's come together and the psi i's come together, just because that's going to make my calculations easy. Okay? And you can already maybe start to see why this is going to make my calculations easy. Because now I can write this. And let's look at this term here first. What do I know about C minus alpha I minus beta I? What must be true at optimality? This is exactly 0. So this entire thing just vanishes, right? I don't need to consider this at all, which is awesome. Right? Okay, great. The next thing, I have this term here. Sigma alpha I yi equal to 0. Is that showing up anywhere here? Right. So I have sigma alpha I yi times W transpose xi, and then I have sigma alpha I yi times B. This has something depending on I, right? But this has no dependence on I. So this is B times sigma alpha I yi. What is that going to be equal to? That's also going to be equal to 0, right? So this I can therefore write, the first term I can't do anything about, minus alpha I yi W transpose xi. And I can just lose this B here entirely, right? Because sigma alpha I yi is equal to 0. Everyone with me? Or maybe should I write this separately? Is this going to confuse people? Are you confused or are you with me? Okay, let me write this way. And then plus or no, minus right? I write this term in two separate things. So I can pull this b out because it doesn't depend on I. So this entire term becomes 0. This does not become 0. It has an I in here. You can't, like alpha I yi times xi, w transpose xi is not 0. Alpha I yi is 0. Sigma alpha I yi is 0. This b only pulls out because it's a scalar. Plus sigma alpha I. Right? Okay, good. Now we have this. Now we haven't yet used this thing, right? But we do have something that is kind of showing up of that similar form here. So this W transpose Xi, can I rewrite this in a different way? Can I write this as Xi transpose W? That's totally legitimate, right? Okay, now I have this summation over I. This depends on I, this depends on I, this depends on I. This, one of these things is not like the others. Does not depend on I, right? So I can pull this out this way, right? And now what do I have? W is equal to sum of alpha I, yi, xi. What do I have here? Alpha I, yi, xi transpose. So what is this quantity equal to? This thing is just W transpose, right? So this I can write as 1/2 But now these things cancel. So this is just minus 1/2 W transpose W plus sigma alpha I. Okay? So I got from something very complicated to something that's actually quite simple. Okay? The thing that's kind of annoying about this is now I have the primal and the dual variables here, right? But remember, I want to find the dual. So when I want to find the dual, is there a way I can actually write this entirely in just the form, in just terms of the dual variables? Well, I actually know W as a dual, in terms of the dual variables, right? So I can rewrite this as minus 1/2 sigma alpha I, yi, xi transpose times sigma alpha I, yi, xi plus sigma alpha I. Okay? And now this is only in terms, so now I have a Lagrangian that is expressible only in terms of the dual variables. Does everyone see that? And there's kind of some nice ways to think about writing this. In particular, I can write this as minus 1/2, and I can write this as, let's say, I write this vector alpha 1, y1, alpha 2, y2, alpha n, yn, times x1 transpose all the way up to xn transpose. This sum is just equal to this dot product. Everyone with me there? Similarly, I can write this as times okay? This thing is just this dot product. So if I call this matrix my data matrix, if I call this matrix capital X, this I can write equal to -1/2. I can write this as, let's say, alpha transpose times y1, yn times x transpose times y1 to yn times alpha plus right? I'm just now using properties of matrix vector multiplication, right? Nothing fancy is happening. But I want to now scale every entry of a vector, alpha, by, I want to scale the ith entry by yi, so I multiply by a diagonal matrix with those weights on the diagonal, right? So that this row vector is exactly equal to this thing. Okay? This matrix, let's look at this matrix. What does this matrix depend on? Now, this is matrix times matrix times matrix times matrix gives me another matrix. Are there any variables in this matrix? Are there any primal variables in there? Are there any dual variables in there? This is entirely data dependent, right? So I can compute this product just by looking at my data. I do not have to do anything else. There's no optimization, nothing. It's just taking my data, stacking it up, and doing a calculation. Okay? I'm going to call this matrix Q. And so I can write this as -1/2 alpha transpose Q alpha plus sigma alpha I. And now I have my Lagrangian expressed entirely in terms of dual variables alpha. Okay? So now my Lagrangian, remember, my dual can be written in terms of my Lagrangian, right? It's a max-min. It's a max over the dual variables first, then a min over the primal variables of the Lagrangian, right? When I look at that expression for my Lagrangian, are there any primal variables in it? No. So when I take the minimization over my primal variables, what do I get? The exact same expression. So now if I wanted to write my dual, right? There are no primal variables. Therefore, my dual is now just the max over alpha and beta of -1/2 alpha transpose Q alpha plus the sum of the entries of alpha I. Okay? You should be feeling a little bit funny about what I'm doing. Are you feeling a little bit funny? I kind of made some assumptions along the way, right? I said that, oh, let's have this relationship between the primal and dual. I said, let's use these KKT conditions. So I need to make sure that all of this is satisfied, right? So I can't just say the dual is that. I have to add the appropriate conditions. And so I have to add all of these things as conditions. So basically, I need to say that sigma alpha I yi is equal to 0. And I need to say that C minus alpha I minus beta I is equal to 0 for every I, right? And then I need to have alpha I greater than or equal to 0, beta I greater than or equal to 0, because these are my dual variables. I don't need to add this constraint. Why do I not need to add this constraint? Because this is saying this is something about relationship between alpha and w, but there's no w in my optimization program. So constrained on w means nothing to me, right? So I could add it, but it doesn't make any difference. So this is the dual program that I get. No, strong duality does hold. We know that this holds for a fact.
Then why do we need those conditions?
We need these conditions because if I was to solve this program without these conditions, I'm missing connections between the variables. I'm not connecting this to my data. Right? This simplification, this Lagrangian, is equal to this expression only if these conditions are satisfied. This Lagrangian is not equal to this expression just every day. It's only because these things, we use these things, right? These properties equations, and therefore they have to be added as conditions to my dual. Okay? Okay, but we can now do some further simplifications to this. In particular, there's not really any beta i's in here, right? So it would be nice if I can kind of, let me just use my space a little bit more efficiently. So taking that, I'm going to keep writing the dual. So I have from this, I know that beta is equal to c minus alpha I, right? Right, we have this. I can rewrite that as that. And I have beta greater than or equal to 0. So if I wanted to just eliminate beta, because there's no beta in the objective function, I can just rewrite this as c minus alpha I greater than or equal to 0, right? Because beta is essentially a dummy variable that's just connecting these two inequalities to each other. Do you see that? So I can just rewrite this as the max over alpha of alpha transpose q alpha plus sigma alpha I. I have to have this sigma alpha I yi equal to 0. And then I have just 0 less than alpha I less than or equal to c.
What happened to the negative 1/2?
Oh, I just forgot to write it. So this is now kind of the standard form of the dual that is used to understand the behavior of the SVM. Okay? So this is kind of the standard form of the soft margin SVM. This is the standard form of the dual of the soft margin SVM. Okay? So this was a lot of algebra, and we usually only do lots of algebra when there's a payoff, right? What's the point? The point is that now we're going to be able to use this dual to be able to do two things. First, we're going to use the KKT conditions, again, to interpret and identify exactly which ones of our support vectors, or which ones of our data points are going to be support vectors. And second, this dual formulation is the very reason that what you might have heard of as the kernel trick can work. And the kernel trick, which we're going to talk about, is the way that you can move from dealing with linearly separable data to also having non-linearly separable things kind of be classified using SVMs. Okay? So the kernel trick is basically the same way that you can do polynomial fitting using least squares, right? And you can fit this polynomial, which is not a linear function, but you can still use a linear technique to fit it by basically saying that, well, my data has these features that are x squared, x cubed, x fourth, so on and so forth. What is unknown is the coefficients, and those are linear. We similarly do something where we change how we look at our data and use that to be able to do SVMs, even though the underlying data might not be linearly separable. Okay? So that's kind of the agenda for the next 25 minutes of class, or 20 minutes, however much time we have left. So we use some KKT conditions here in identifying and computing this dual. What's the other interesting KKT condition that we didn't use? Primal feasibility and dual feasibility are kind of the more boring KKT conditions. They're necessary and sufficient, but they're the less interesting one. What's the other interesting one that we didn't use? Complementary slackness, right? So let's write these out. So we have that alpha I times 1 minus psi I minus yi times right? That's the thing corresponding to this first constraint, right? The dual variable corresponding to this is alpha I. So this product must be identically 0. And then the dual variables corresponding to the psi i's are beta i's. So I must have beta I times psi I equal to 0, right? So these are two more equations that I have, okay? And now I want to come back to this equation that we had here, okay? I want to remember that we knew these three things as well. And in particular, our motivation was figuring out which of our training data points matter, right? And if you look at this W, it's a sum of some of these things. But if you look at this equation, what would make you not care about a training data point? What information would you say says, I don't need to care about this, it doesn't affect my optimal W? If I knew something about the alpha i's, are there some i's that I would care about more than others if I knew something about the alpha i's? If alpha I is 0, does that training data point matter? Does it show up in the optimal W? No, right? Alpha I is a dual variable. Dual variables being 0 or non-zero are very connected to complementary slackness because it tells us about which constraints are active, which constraints are not active, things like this, right? So do you see how complementary slackness can help us maybe figure out which training data points are going to matter and which ones are not? Are these dots starting to, different things that we've been talking about are starting to connect somehow? Yeah? Okay, good. So now, if we look at this, let's consider the following setup, okay? First, let's say alpha I is not equal to 0, okay? That means that that training data point is showing up in that optimal W. And let's further consider the case that 0 is less than alpha I is less than C, okay? What can I conclude from this? I know that C is not equal to alpha I, and I know beta I is equal to C minus alpha I, okay? So if I assume alpha I is distinct from my constant C, what does it tell me about beta I? Beta I is therefore not equal to 0, right? If beta I is not equal to 0, what can I conclude about psi I? This implies that psi I must be 0, okay? What is the interpretation of psi I? Psi I tells me, is there a margin violation or not, right? Psi I is the amount of encroachment that I have into my margin, right? I have my W transpose X plus B is equal to 1 line, right? These are my things. And the psi i's are telling me, like let's say I have some triangle point here, how much am I violating my margin, right? That's what it's telling me. So if the psi I is 0, what does that mean for the ith point? Is it violating the margin? No, right? It's either exactly on the margin, or like could be further away, right? But now further, right? I know that alpha I is not equal to 0. What does that mean about this? 1 minus psi I is actually exactly equal to yi right? Because alpha I is not equal to 0, this must be equal to 0. Therefore, this must be equal to this. Everyone with me? Alpha I is not 0. Therefore, this second term must be 0. If this term is exactly 0, this minus this is 0. Therefore, this must be equal to this. Right? Psi I is 0. Therefore, 1 is equal to yi times w transpose xi plus b. But what does this mean about the ith point? Where does it lie? Exactly on the boundary, exactly on the margin, right? It's exactly here or exactly here. Ith point is exactly on the margin. Furthermore, alpha I is not equal to 0, so it's mattering, right? This is a support vector. I'm just saying, let's take this case. Let's assume this. Let's assume this case. So case 1. Okay? Basically, what I'm saying is that by looking at the dual variables, let's say I solve this dual, I get the values of alpha i's. Now I want to use this to implement my classifier, right? By looking at the values of the alpha i's, I can identify whether or not they're less than c, greater than c, whatever, right? I've solved the dual. I know all the numbers now. But basically what I can say is that for any point I such that alpha I is not equal to 0 and alpha I is not equal to c, that point must be a support vector. It critically matters in the positioning of the classifier. If you change this vector, if you change this training data point, your classifier will change. Okay? Does everyone understand this case? On the margin. So remember, I have like my triangles up here and my circles up here. Where I have some triangles, 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 circle, 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 circle. And I'm trying to find this separating hyperplane. So I'm trying to find a hyperplane that says all the triangles are on one side, on the positive side, and all the circles are on the negative side. Okay? And remember, I'm trying to maximize my margin, right? That's what I'm trying to do. So the margin is exactly this, because remember we set the magnitude of w to be equal to 1 over m, right? M was our margin, but we normalized it so that basically this margin is going to be exactly at 1. Okay? And so on the margin means that you're exactly this unit 1 away from your separating hyperplane. Violating the margin means you're inside this boundary, this no man's land. Okay? And otherwise, you're kind of outside and you don't even really matter. The question was, we chose a particular normalization for W. If we had chosen a different normalization, we wouldn't be able to do all of this interpretation. You could still do it, but not in the exact way that I'm doing. You could still have a completely valid interpretation. The dual would still work out to be nice. But your constants would be different. Right? Your two margins wouldn't be W transpose X plus B is equal to 1. It would be different, because based on how you normalize this. These are all vectors. So now there's, of course, the other case where alpha I is not equal to 0, but alpha I is equal to C. Right? If alpha I is equal to C, then I cannot conclude that, I can conclude, in fact, that beta I is equal to 0. Right? Therefore, psi I, the slack variable, maybe is equal to 0, maybe it's not equal to 0. Right? Here we use this kind of beta I not be equal to 0 to conclude psi I must be equal to 0. But now, since beta I is equal to 0, we can't really conclude this, right? Maybe it's equal to 0, maybe it's not equal to 0. Okay? So basically, we don't really know much about what to do, like these psi i's. Maybe it's on the margin, maybe it's violating. We don't know. This alpha I not equal to 0 means that it still does matter. Right? And so these are still points. Basically, anytime your alpha I is not equal to 0, that's a point that matters. That's something that you're going to count as a support vector. But you don't know now whether this is exactly on the margin or it's violating. It could go either way. Okay? So ith point could be exactly on margin, or it could violate. Okay? And the last case now is now, let's say, alpha I is equal to 0. Okay? So we're taking cases now alpha I. We have 3 cases. One is equal to 0, one is not equal to 0, and when it's equal to 0, when it's not equal to 0, we're doing these 2 subcases, right? If alpha I is exactly equal to 0, we know it doesn't show up. Right? That ith training data point doesn't show up in the optimal W. It doesn't matter in this calculation. Okay? This implies that beta I must be equal to exactly C. Right? And we know C is not equal to 0 because we're choosing it. So we know beta I is now distinct from 0 again. This means that psi I, again, is equal to 0. Okay? Which again means, is this point going to matter to us? Right? Slack variable, if psi I is 0, could my data point be exactly on this margin? It could. Could it be here? Could it be here? Could it be here? Could it be here? Could it be here, inside the margin? No. So this point, such points never violate margin. Do not affect the classifier. Okay? So these are the non-support vectors. These are the things that you're basically going to throw out and say, this training data isn't that important to me for finding my classification boundary. So I don't have that much time left, but I really want to tell you about this kernel trick. So I'm going to kind of push forward a little bit. Okay? So now I'm looking at this dual formulation here, right? And when I'm looking at this, let's say I have data that is of the following form. This is excess here, and some circle points here. Is this data linearly separable? It is not linearly separable, right? But does it seem to have some kind of structure to it? It does, right? Instead of thinking of this, for example, this is, let's say, the x1 axis and the x2 axis. If I thought of these data points as a function of x1 squared plus x2 squared, or even just x1 squared and x2 squared, right? If I could think about this as a bowl, right? If I could project these into 3 dimensions, right? Then can I think of this as a bowl where the kind of x's are down at the bottom, but the circles are going up at the top, and then if I had these points down here and points down here, I could have a linear separating hyperplane that kind of cuts between these two, right? So if I can project this data into a different appropriate space, I might be able to make the data linearly separable, okay? And that is what using kernels is about in the context of SVMs, okay? So one of the nice things about the SVM is that when you look at this dual formulation, right? When I'm trying to compute this Q matrix, all that matters is this product of my features. So I have this x times x transpose, right? So I'm basically looking at x1 transpose times x1, x1 transpose times x2, these kinds of dot products when I'm looking at my x1, x2. And so if I have some vector, if I had a vector, let's say x1, x2, xn, and I wanted to transform it, let's say, into something that was x1 squared, x2 squared, xn squared. Let's say hypothetically I wanted to transform it into something like this, right? I can do that, and all that's affected in my dual is this Q matrix, right? And in fact, I don't even need to necessarily do this transformation explicitly. All I need to know is this product XX transpose. Okay? So what the kernelization allows you to do is it allows you to be able to think about, instead of your features being x1, x2, x3, x4, think about them as being functions of x1, x2, x3, x4. So a common thing that people like to do is think about polynomial functions. So think about, for example, the entries of the vector x, or the feature vector being like all degree 2 polynomials of x1 and x2. So for example, a common thing to do is if I have this x1, x2, I transform it into x1 squared square root 2 x1, x2, x2 squared, something like this. And the nice thing about there's these sets of functions that are called kernels that basically this product, this x transpose product, is very easy to calculate. And if this is very easy to calculate, then solving the dual is very, very simple. And so what you can do is basically you can use this to fit non-linearly separable, or data that is not linearly separable, but to still be able to get an SVM to work for it. So I'm just going to show you this in the context of a demo. Point being that you can use different kinds of kernels to be able to separate basically this kind of data. And the way you do it is one of the reasons why SVMs are so powerful. So we didn't have enough time to talk about it today. This is my last lecture, so I will not be here lecturing. If I'm still able, I might still come to class and listen to the guest lecture, but I just don't know where it'll be. You've been a great class. I'm sad to end this particular semester. I think it's been a particularly high energy and very positive class atmosphere that I've particularly enjoyed. So thank you very much for being a great bunch. And if you have time, I would really appreciate if you filled out course evaluations at some point. It really matters for kind of feedback for the course, and we try every year to update things. Like this semester, we have lots of changes to the projects based on feedback we got last semester. So it really, really helps, and it's an important thing that people consider when for faculty evaluations and things like that. So would really appreciate if you filled out the evaluations, particularly also for your TAs. I'm just one person up here kind of doing my thing, but the heart and soul of this class is your TAs, and they're beyond fantastic. So if you ever get a chance to say thank you, please say thank you to them, just a short email. It really, really makes a difference to particularly the TAs. So, you know, any kind words you have to send their way, that's what really, really, really matters to me. So if you get a chance, just say thanks to them, okay? Thank you again, and I will hope to see you next week, but in case I don't, best of luck, okay? Thank you.